Assalamualaikum. I introduce you to the solution of the angular part of the Schrodinger equation for the hydrogen atom. The key is that we could separate the wave function into, which depends upon radius theta and phi, into a radial part which depends only on r, a polar part which depends only on theta, and an azimuthal part which depends only on phi. This was easy to solve. This was very easy. Out of the Schrodinger equation, we formed three equations by virtue of the separation of variables technique. Now let me write those three equations for you. The first equation was 1 over capital phi d square capital phi function of small phi d phi square equals minus ml square. The first equation, the azimuthal equation. You don't have to remember this, but it will be useful if you could go through the derivation on your own, which I already initiated for you. So this was our azimuthal equation. And then we have a polar equation which goes as follows: ml squared sine squared theta minus 1 over capital theta sine theta sine theta L plus 1. This is our polar equation. And our third equation is the radial equation, which depends only on the radius r. So starting from the Schrodinger equation, we have these three equations and we have to solve each one of them. I solved the first equation for you. The second equation, I've written up the solution for you, and I expect you to go through the solution and the derivation. This third equation we will not solve. Interested readers can look up an appendix in the book. Now, what do these equations mean and what are the results of these equations? Now we know that the wave function has a radial part, a polar part and an azimuthal part. So let's focus on the angular parts only first. And the angular parts are of two kinds, the azimuthal part and the polar part. So the angular part of the wave function comprises a theta and a phi. Now we already know what this function is. This function is what is phi? We derived the solution. नोट्स देके मुझे बताइए कि व्हाट इज फाई। जो रेड जर्सी में बैठे हुए बताइए कि आप बताएं व्हाट इज कैपिटल फाई। Small phi?
Yes.
So this is the azimuthal part of the solution. And what are the constraints on ML? बताओ। ML जो आपका दिल चाहे वैल्यू ले लें आप। जी? रियल नंबर होना चाहिए बस। Integer होना चाहिए. It could be a positive integer. It could be a negative integer. Can it be zero?
No.
Yes, ML can be zero. So ML is an integer, positive or negative. And where does this constraint come out from? आप बताइए, आप फोर्थ रो में जो बैठे आप बताइए जी, ये कॉन्स्ट्रेंट कहाँ से आया है ML को? बिल्कुल आइडिया नहीं। पिछले लेक्चर में मौजूद थे आप बताएं साथ। So the wave function has to be single value. You come to the same value of phi, that is if phi is 30 degrees. If phi changes from 30 degrees to 390 degrees or from 390 to 390 plus 360 degrees, you are coming back to the same value of phi. The wave function must remain the same. In other words, the wave function has to be single value, and that is why ML has to be an integer. Now this polar part is something we also derive. Now if you notice in the azimuthal part, the solution depends upon the value of ML. So I can write a small ML here. Phi sub ML. Now theta depends upon ML and it also depends upon L. Let's draw a table. We know that ML can take up integer values. It could be 0, plus 1, minus 1, plus 2, minus 2, plus minus 3 and so on. And we also know that L plus ML modulus, sorry, N max plus ML modulus has to be equal to L. And N max is also an integer. So combining both of these conditions, we reach the conclusion that ML, the maximum value of ML modulus is equal to L. Because N max can be 0. So where does this condition come from? This condition came out of a solution of the polar equation, and we noticed that if we look at a series solution, the solution must have a finite number of terms, otherwise the solution diverges and the wave function becomes unrealizable. So both of these conditions are imposed by the legitimacy of the wave function. Now what do these conditions together mean? They mean that L has to be greater than ML modulus. because n max is a positive integer. Therefore, L has to be greater than ml max. So combining both of these conditions, we get the following: ml modulus has to be less than or equal to L, and both of them are integers. In other words, for a given L, the possible values of ml are, starting from 0, they can go all the way up to L, and on the negative side they can go all the way up to minus L. So for a given value of L, there are 2L plus 1 possibilities of ml, and these conditions come out because our wave function has to satisfy certain conditions. A third condition is that now how many dimensions is this problem set in? It's a 3-dimensional problem. How many quantum numbers do you expect? You expect, जब हमने 3-dimensional infinite well किया था, कितने quantum numbers आए थे? बताओ, रेड टी-शर्ट में 3 quantum numbers आए थे, जरा एतमाद से बात करो। और 1 dimensions में कितने quantum numbers थे? 1. In 3 dimensions, we expect 3 quantum numbers. In a 3-dimensional infinite well, those quantum numbers were called nx, ny, and nz. And each one of them was quantizing a certain variable. This was quantizing the x momentum, the y momentum, and the z momentum. In this 3-dimensional problem for the hydrogen atom, we also expect 3 quantum numbers. One of them is L, the second one is ml, and there is a third one which is n. And this n comes out from solving the radial part. And there is a constraint between n and L. And the constraint is that for a given L, for a given n, L can vary from 0 all the way up to n minus 1. So we have 3 quantum numbers, n, L, and ml. N is called the principal quantum number, L is called the azimuthal quantum number, and ml is called the magnetic quantum number. And each one of them has a physical significance which we will discuss shortly. But we have 3 quantum numbers, and there are constraints on these quantum numbers which come out because the wave function has to satisfy certain properties. अब हम ये देखते हैं कि for a given value of L and ml, what are the angular parts of the wave function? What is the polar part and what is the azimuthal part? This is something that is clear because the derivation is easy and the solution is simply exponent iota ml phi. This is, I have shown you how to solve the polar part and obtain the difference. Constant की भी बात है. Suppose L is 0. I also draw a column for n. When n equals 1, L has only one possibility, 0. ML has only one possibility, 0. So what is the azimuthal part of the wave function for ML equals 0? 1. Exponent of 0 is 1. So I can write a 1 here. And the polar part is also constant. It does not depend upon theta. You can look up the solution that I have provided. So I write a 1 here. Something that is independent of theta and phi. There is no theta dependence, there is no phi dependence here. Theta is proportional to 1, phi is proportional to 1, Of course, there is some normalization constant as well, but I'm just writing the angular part. There is some normalization constant as well, because the normalization has to come with r when you write a complete wave function. So theta is proportional to 1, phi is proportional to 1, and the angular part of the wave function will just be a constant, 1 times 1. Now let's go to the next level, that is to the n equals 2 level. For n equals 2, L can be 0, and when L is 0, ML is 0. But L can also be 1. If you look at this constraint, L can go all the way up to n minus 1. Since n is 2, L can go all the way up to 1. But when L is 1, ML can take up 3 values. It could be 0, it could be plus 1, and it could be minus 1. Now let's write the wave function. We're talking only about the angular part of the wave function. Phi is very easy. Phi here is 1, 1. But what about ML plus 1? Exponent iota phi. Exponent iota phi. Exponent. What should I write here? Minus iota phi. Now we observe that the azimuthal part changes by changing ML. It changes by changing ML. So I can write a small ML here. Just to point out, highlight the fact that phi depends upon ML. Alright, now what about L equals 0 and ML equals 0? And what about L equals 1 and ML equals 0? L equals 0 would give you 1. The same as what we have here. Because both L and ML are the same, so theta must be 1. Must be a constant. 1 ka matlab constant. There is no dependence on theta. Now here L takes the value 1 and ML is still 0. Now if you perform the solution which I have already provided, then this is some function of theta and the value is cosine theta. You get cosine theta here. You solve the polar part, your result is cosine theta. 1 plus 1 gives you sine theta. 1 minus 1 gives you again sine theta. Now how do you get the cosine theta and sine theta? For this you will have to perform the long tedious calculation, for which I provided a glimpse in our previous lecture on Friday. Sine theta और cosine theta वहाँ से आ रहे हैं. अब theta changes when the value of L changes as well as when ML changes. So theta now depends on L as well as ML. And of course it's a function of small theta. But it is characterized by these quantum numbers L and ML. So this is the polar part. Now what about n equals 3? ये रिलेशनशिप जब आप रेडियल पार्ट सॉल्व करते हैं इक्वेशन में वहां से for n equals 3, L can be 0, L can be 1, L can be 2. When L is 0, ML is 0. When L is 1, ML can be 0 or plus minus 1. 2 can be 0, plus minus 1, plus minus 2. So these functions will be the same as this, because L and ML are the same. The polar parts do not change. So 0, 0 will give you the same row as this, 1, 0 will give you the same row as this, 1 plus minus 1 will give you the same row as these. Now when L is 2, you can fill up these rows on your own. When L is 2 and ML is now 0, now this is a different combination of L and ML. You can quite easily write the azimuthal part. The azimuthal part here is 1. Here it's exponent plus minus iota phi, and for ML plus minus 2, the azimuthal part is exponent plus minus iota 2 phi. प्लस के साथ प्लस, माइनस के साथ माइनस, और जो पोलर पार्ट है यहां पे आएगा 3 कोसाइन स्क्वायर थीटा माइनस 1, यहां पर आएगा साइन 2 थीटा, और यहां पर आएगा साइन स्क्वायर थीटा. So these come out of a solution of the angular part of the Schrodinger equation. Now both of these parts, the theta part and the phi part, together give you the angular part of the wave function. They give you the angular part of the wave function. Now let's try plotting these wave functions. Let's try plotting these wave functions. Let's first of all suppose L is 0. What is ML? 0. So what is theta? Right? This is the angular part of the wave function. एक रेडियल पार्ट भी होगा जो अभी हम कंसिडर नहीं करें. ये एंगुलर पार्ट है वेव फंक्शन का. दिस डिपेंड्स ऑन ml, दिस डिपेंड्स अपॉन l, ml. L is 0, ml is 0. So this is proportional to what? It's just a constant. Now the combination of theta and phi, the combination of theta and phi with a particular value of L and ML is given a special name. It is denoted as capital Y. It's denoted as capital Y. It's characterized by L and ML, and this Y depends upon theta as well as phi. It's just given a special name, this function. So this function is called a spherical harmonic function. It's a very important function in all branches of science and engineering and electrical engineering. So this function, which is a combination of theta and phi, is denoted by capital Y, and it depends upon L and ML and varies as theta and phi. Okay, it will have a theta dependence and a phi dependence. Now this is a wave function, or at least one part of the wave function. The modulus squared of this function will give something that is proportional to a probability density. Agreed? So let's take Y, L and L, theta phi, and let's take the modulus squared of this, which is simply Y, L, M, L, theta phi complex conjugate multiplied by the normal function. So this is just the square of 1. So this is proportional to 1. Now I want to plot this probability density. This is like a probability density. So what I do, I make a special kind of diagram which is called a polar diagram. Now how do I draw a polar diagram? I'm a three-dimensional being, but this blackboard is two-dimensional. So there is a certain limitation in drawing polar diagrams. The easiest solution is you make a plane. This is your z-axis, and as you go down from z-axis, theta changes. That is, on the z-axis, theta is 0. On this particular axis, which I call the y-axis, this is the z-axis, this is the y-axis. On the y-axis, theta is 90 degrees. In between, theta is between 0 and 90 degrees. I go to the minus z-axis, theta turns out to be 180 degrees, and so on. So for this particular function, does it have any dependence upon theta? There is no dependence on theta. It's totally spherically symmetric. There is no dependence upon phi. Now on this plot, the distance from this origin denotes the value of the function. So in a polar plot, the distance from the origin, how far away I am from the origin, denotes the value of the function. Now the value of the function is constant at 1, no matter what the value of theta is. So what will the polar plot look like? It will just be a circle. The polar plot is simply a circle of constant amplitude or constant radius and no dependence upon theta. So you change the value of theta, this remains a circle. Now since this is a three-dimensional function and I have only projected onto a two-dimensional plane, I have to twist about the z-axis. I would like to twist this diagram about the z-axis. And when I twist this diagram, this circle about the z-axis, what do I get? I get a sphere. So this is really a sphere. And this represents the probability density of finding an electron that has L equals 0 and as a result ML equals 0. Therefore, if I have an electron inside a hydrogen atom with a quantum number L equals 0 and hence ML is equal to 0, then the probability density function for such an electron will be totally spherically symmetric like a sphere, and there will be no dependence upon theta or phi. Therefore, if I am standing at a particular radius and the electron is standing at a particular radius and the electron decides to move on the surface of a sphere without changing the distance from the nucleus, its environment remains unchanged. So the electron has equal probability of being located at any point on the surface of a sphere. Remember, we are not talking about the radial part of the wave function. If we talk about the radial part of the wave function, the probability may decrease as we go out in radius, that is further away from the nucleus. Right now we are only talking about the angular part. So this kind of arrangement is called an s orbital. So this is an s orbital. This L equals 0, ML equals 0 is an s orbital. Likewise, this will be an s orbital. So you can have an s orbital in n equals 1, n equals 2, in n equals 3. It's also called an s wave because this is really a wave function. It's a matter wave corresponding to the electron. So this is one way of drawing the probability density, which is the modulus squared of the spherical harmonic function. And for L equals 0, ML equals 0, it just reproduces a spherically symmetric distribution. Now what does this physically mean? This means that if the electron is in the s orbital and you want to find the probability you want to find where the electron is. You perform an experiment, the electron can be present on the surface of a sphere. You perform an identical experiment on an identical atom, the electron will be present somewhere else on the sphere, and the probability distribution will be constant at any point on the sphere. So you can detect the electron anywhere on the surface of a sphere with equal probability. And the s orbital is totally spherically symmetric. Now let's move on to our next candidate on the level of complication. This is higher, that is L equals 1 and ML equals 0. And let's draw a polar diagram for this particular state, L equals 1 and L equals 0. और जो उसका wave function का angular part होगा will be proportional to cosine theta. Let's plot this on our polar diagram. L equals 1, ML equals 0. Why? L is 1, ML is 0, theta phi, which is simply capital theta, 1, 0, small theta, capital phi, 0, phi. This is simply proportional to cosine theta. Just multiply cosine theta by 1. Remember, there is a proportionality, there is some constant here as well, which is immaterial for the polar diagrams we are plotting. So if I take the modulus squared of y10, this will be proportional to cosine square theta. Now notice there is no dependence on phi because ML is 0. There is only dependence upon theta. Now let's plot this on our polar diagram. Y-axis, Z-axis. This is the theta equals 0 axis, this is the theta equals 90 degrees axis. Now when theta is 0, this function is maximum. So it's maximum somewhere here. And as theta advances towards 90 degrees, this is the theta 90 degrees axis. As theta advances towards 90 degrees, this function decreases. And it finally goes to 0 at theta equals pi by 2. So if I plot this cosine square theta, I get this. And then I can go from theta pi by 2 to theta equals pi. At theta equals pi, cosine of pi is minus 1, cosine square of pi is again plus 1. So this distance is the same as this distance. So this is the range of possibilities for theta. But theta can also be in the opposite direction. So I can complete this figure, and this is how the figure is completed. So this is a plot of y10 modulus squared. I am plotting the probability density here, the probability density function. Suppose I wanted to plot not the probability density function but the wave function. That is, suppose I wanted to plot y10. Y10 is proportional to cosine theta. Let's plot the wave function, not the probability density, on a polar diagram. Y. This will simply be a cosine curve, that is something like this. With the difference that when theta is between 0 and pi by 2 and between minus pi by 2 and theta, you get a positive number here. Right? You get a positive number here. So this lobe is positive. The wave function in this region is positive, whereas the wave function in this region is negative. यहाँ पे wave function positive है, यहाँ पे wave function negative है, and this is simply the cosine function. Now if I take the square of this, which is the probability density, I achieve a probability density function which is the square of a cosine, and you have a positive probability density everywhere. So I plot the wave function in books, in textbooks, in chemistry books. When you plot this wave function for what is called a p orbital, because L is 1, then one of the lobes is shown differently from the other lobe because one is positive and the other is negative. But when we talk about probability densities, you get a positive probability density function everywhere. So this kind of arrangement, that is this kind of probability density which corresponds to L equals 1, ML equals 0, you can immediately recognize it's an orbital. What kind of orbital is it? It's a p orbital, and it's called a pz orbital. So this is a pz orbital. So there are different ways of plotting wave functions and probability densities. This is a pz orbital. This is a polar diagram. Another way of plotting a probability density is through an electron cloud. An electron cloud means that you have a scatter of points and the points are scattered densely where the probability density is higher. That is, when you measure the location of an electron which exists in a pz orbital, most of the time the electrons will be found close to the z-axis. And this scatter plot or this electron cloud plot shows you where the electron is most likely to be found. Alright, and remember one thing. There is a node here. The wave function goes to 0 here. This is a node. The wave function goes to 0. You cannot find the electron, you can never find the electron that is in a pz orbital to exist at the node. But there is a positive probability density above this plane, which is called the nodal plane, and the positive probability density below the nodal plane. So how does the electron get across the node? Stop thinking of the electron as an object in motion. The electron is not an object that is moving from above this nodal plane to below the nodal plane, and from below the nodal plane to above the nodal plane. This is a picture of the electron in one go, in one shot. You have an electron, you haven't measured it. The objective reality of an electron is that it exists everywhere. It exists wherever this probability density function is non-zero. However, when we measure the electron, we perform an experiment, you collapse this wave function. You collapse the entire field onto a single point. You perform the experiment again on a clone, on an identical copy of the electron in the same orbital. You will get a different point. That is the randomness. But before you are making a measurement, this is a picture of one electron. And it's not an electron in motion. Therefore, asking the question, how does an electron get across the node, the question in itself is flawed. So this is a picture of a pz orbital. Now I've drawn the orbital on a two-dimensional blackboard, on a two-dimensional surface. In fact, in order to complete the picture, I have to twist this diagram so that I twist it around the z-axis, and the total picture I get is two dumbbells. Right? I get a three-dimensional object which looks like a ribbon, like this. Y, X, and Z. So this is my pz orbital, and it comes up naturally from solving the Schrodinger equation. This is a wave function, not probability density. The wave function can be negative. Point in time. Alright, beautiful, very nice question. Suppose an electron is in the pz orbital. देखो ये वाला ऑर्बिटल, ये वाला कॉम्बिनेशन क्वांटम नंबर्स का 1 0, दिस इज कॉल्ड pz orbital. This combination 1 0 is a pz orbital. Now the question this right student has asked, if you have an electron and you constantly track the motion of an electron, that is the electron is under the vigilant eye of a microscope, ठीक है, इलेक्ट्रॉन को आप इलेक्ट्रॉन माइक्रोस्कोप के तहत या किसी भी तरीके से आप उसको कॉन्स्टेंटली ऑब्जर्व कर रहे हैं, दैट इज यू आर मेकिंग अ कांस्टेंट मेजरमेंट. व्हाट हैपेंस? कॉन्स्टेंटली मेकिंग अ मेजरमेंट. देखो एक फेमस मकूला है इंग्लिश का, अ वॉच पॉट नेवर बॉइल्स. क्या मतलब इसका? कि अगर आप अंडे उबाल रहे हैं, आपने पानी रखा हुआ चूल्हे के ऊपर, अगर आप चूल्हे को देखते रहें और अंडे उबलने का इंतजार करते रहें, अंडा उबलेगा नहीं, ज्यादा देर लगेगी इसमें. ठीक है, द सेम adage can be applied here. A watch pot never boils. You are observing the electron, you are projecting the electron onto a certain point on this certain point in this three-dimensional space. You're projecting the position of the electron. You're finding where the electron is. Now you're constantly observing it. You're constantly shining photons on it. That's what you're doing. When you want to observe the position of an electron, you're constantly looking at it. The electron will remain where it is. You're constantly projecting the position of the electron. In other words, you have a wave function, you collapse it onto a point, and then the point remains a point, and you are constantly observing it. The electron will remain where it is. The position of the electron will not change. The point will remain a point. It will not evolve back into a wave function. It will remain a collapsed wave function. This is called, in quantum mechanics, Zeno's paradox, or the Zeno effect, sorry, the Zeno effect. The Zeno effect means, in the quantum world, a watch pot never boils. You are constantly projecting the position of an electron, it will remain where it is. That's what you will measure. This is a postulate of quantum mechanics. Interested students who will study quantum mechanics will learn that when you have a wave function, you collapse it. You measure it again, you are collapsing it again. When you are collapsing the wave function, there is a new wave function that is formed, and that is the collapsed wave function. And the collapsed wave function becomes the initial condition for a next measurement. So the answer to your question is the electron will keep its position where you measured it for the first time. Now when you have another electron, you measure the second electron, it can have a different position. But once you start measuring the second electron, it will remain where it is. So even in this case, you will never find the electron to exist on the node. Now, let's go to our next level, which is the L equals 1, Mn equals plus 1 level. Do you expect this to be a px orbital? It could be a px or a py orbital. Let's see which one of it really is. Now when L is 1 and Ml is plus 1, y plus 1 is proportional to sine theta ei phi. Now we can't plot this wave function because it's a complex number. We can plot the real part and the imaginary part, but let's not plot the wave function itself, rather let's try plotting the probability density. The probability density will be the modulus squared of this. Okay, अब मैं जिससे पूछूं वो मुझे बताए कि इसका मॉड्यूलस स्क्वायर्ड क्या होगा. आप बताओ. साइन स्क्वायर थीटा, ठीक है. because this term, the complex conjugate, will multiply with this and cancel out. So you will get sine squared theta. Now plot this on a polar diagram. इसको प्लॉट करना है. At theta equals 0, the probability density is 0. At theta equals 90 degrees, the probability density maximizes. And in between, as you go from here to here, you follow sine square curve. This is what you would get. So is this a py orbital or a px orbital? Py orbital. Is there any phi dependence? I could have drawn another diagram in which this for the x-axis and this for the z-axis, and I would have obtained a similar diagram. So now is this an x or px orbital or a py orbital? It looks like a px orbital. So which one of these? Is this a px orbital or a py orbital? In fact, I have to twist this around the z-axis in order to complete the picture. And when I rotate this or revolve this around the z-axis, I do not get lobes on the y-axis or the x-axis. I get a donut shape. Okay, I get a donut shape, something that looks like this. I get in 3 dimensions. I just revolve this surface. I get a surface of revolution. I revolve this plane. I get a flower kind of arrangement. I get a floral kind of shape. So this is not an x orbital or a y or px orbital or a y orbital. This is simply this spherical harmonic function, and the other spherical harmonic function corresponding to -1 will give me the same polar diagram. So now there are two functions, two different functions with the same probability densities, and we will notice later that they have the same energies. So how do I construct px and py orbitals out of this? आपका पहले एक सवाल था, वो उसका जवाब. देखो z axis की get twist. देखो, there is no phi dependence here. There is really no phi dependence in the probability density. Therefore, this diagram has to be independent of phi. Whatever the value of phi, I should get the same probability density. Therefore, the lobes are not on the x-axis or on the y-axis, they are everywhere in the equatorial plane. So this is neither a px orbital or a py orbital. In order to construct what chemists call a px orbital or what chemists call a py orbital, I have to do something else. देखो, ये जो फंक्शन है ये वाला, ये है y1 1 और ये फंक्शन है y1 -1. This is the spherical harmonic function y1 1. This is y1 -1. Let's add the two functions together. If we add y1 1 plus y1 -1, we are adding the wave functions. Remember, wave functions are simply waves. Wave functions are waves and they can interfere. So what we are doing, we are adding two waves. These are matter waves for the electron and we are adding these waves before taking the probability density. Very important fact. Before taking the probability density, we are adding the waves, and when we add the waves, we will get sine theta E I phi plus E minus I phi, and this will be proportional to sine theta cosine phi. Now let's subtract the wave functions y1 1 minus y1 minus 1, and let's you get sine theta E I phi minus E minus I phi, and I get something that is proportional to sine theta sine phi. Of course there is an iota as well, but I am only writing proportionality here. So let's make a polar diagram for this function and a polar diagram for this function. Now there is a phi dependence. Notice this. I call this function 1 and I call this function 2. I make a polar diagram for 1 and I make a polar diagram for the function 2. Now the function number 1 depends upon phi, and this is maximum when phi equals 0, which is the x-axis. So I can write the x-axis here and the z-axis here, and I plot it. I plot the modulus squared of this function. This is what I get. And for function number 2, which is maximum at phi equals pi by 2, I plot the y-axis here and the z-axis here, and I plot the modulus squared. Of course, I am plotting the modulus squared. So this is sine squared theta sine squared phi. This is sine squared theta cosine squared phi. Now in this particular diagram has its lobes on the x-axis, and if I change to the y-axis, that is I change phi becomes pi by 2, the probability density disappears. So if I look from the top, if I look at this probability density from the top, I have an x-axis and a y-axis, and I'm looking at this probability density from the top, there are lobes only around the x-axis, because on the x-axis phi is 0, on the y-axis phi is pi by 2. But if I make phi equals pi by 2, that is I go here, the probability density must go to 0. Therefore, I have broken the symmetry. I no longer have a dumbbell or a donut in 3 dimensions. I have lobes only centered around the x-axis. And in this case, if I plot this by viewing this probability density from the top, x-axis goes here, y-axis goes here, and I am looking at it from the z-axis, then the lobes will be centered around the y-axis. This is what chemists call a px orbital. Px orbital. And this is what chemists call a py orbital. All right. So this is not really a px orbital. Even though L1 Ml0 is a pz orbital, L1 Ml plus 1 is not a px orbital, what chemists call a px orbital. Rather, the combination of y1 1 plus y1 minus 1 is a px orbital, and the difference of these wave functions is a py orbital. And there is really no difficulty in understanding this, because all three of these orbitals, or all four of these orbitals, they have the same value of n. They have the same value of n, and we will learn later that energy depends upon n. So all four of these orbitals have the same energy. And when all four of these orbitals have the same energy, it's a degenerate state. So all four of these orbitals have the same energies, and you can make combinations of the wave functions without any problem. You can mix these wave functions, you can add waves. Or in other words, think of this in this fashion. Is this a solution of the Schrodinger equation? Yes. For a given radial part, this is a solution of the Schrodinger equation. Is this a solution of the Schrodinger equation? Yes. Both of them separately are solutions of the Schrodinger equation, legitimate solutions. Is their combination, is the linear combination also a solution of the Schrodinger equation? Yes. So we can make any combinations we like of the solutions, and the new function will in itself, on equal footings, be a legitimate solution of the Schrodinger equation. So there is no prejudice that we must have in favor of this over their linear combination. This is also a legitimate solution. Their difference is also a legitimate solution. When physicists talk about orbitals, they generally talk about this wave function. But when chemists talk about wave functions or orbitals, they take their combinations. And this is what is meant by a px orbital and a py orbital. Therefore, from the Schrodinger equation, and by solving the Schrodinger equation, we have reconstructed the s orbitals, we have reconstructed the p orbitals. Now let's look at one of the d orbitals. Very interesting. Let me finish, then I'll answer your question, because otherwise we'll run out of time. If it's brief, okay. कोई भी आप combination बना सकते हैं. You can put an iota here, a minus iota here. You can make any combination that you like. But the polar diagrams will then become very messy, and they will become non-aesthetic. You see, physics is couched in language, and you have to make pictures to represent what you're talking about. And there is always an aesthetic sense to what we're talking about. So making these combinations imparts an aesthetic and a pleasing look to the wave function. You can make any combination that you like. Mathematics does not care about aesthetics or ugliness, but physics sometimes does. So in order to make the px and the py orbitals, you have to make these neat, clean combinations. Otherwise, you can add an iota here, a minus iota here, you can add an under root 2 here, any combination that you like. It's still an orbital. Now let's look at this function. इस फंक्शन को देखते हैं. ये जो सारे पॉलिनोमियल्स हैं ना, इनको लेजेंडरी पॉलिनोमियल्स कहते हैं. These are all legendary polynomials. Now let's look at L equals 2 and ML equals 0. 3 cosine square theta minus 1. अपने दोस्तों को मोबाइल पर कह दें कि बस 5 मिनट रह गए. अच्छा, इसको प्लॉट करना है पोलर डायग्राम पर. तो इसको प्लॉट करने का आसान तरीका ये है, इसका y20 is proportional to 3 cosine square theta minus 1. It does not have any phi dependence. Okay, it's spherically symmetric, does not have any phi dependence. It's azimuthally symmetric, sorry. Now I want to plot the modulus squared of this. 3 cosine square theta minus 1 whole square. इसको प्लॉट करते हैं. तो आपकी जिंदगी आसान हो जाएगी जब आप पहले इस फंक्शन को विद रिस्पेक्ट टू थीटा प्लॉट करें। थीटा बाय 2 0 इसको प्लॉट करें तो आपके पास क्या आएगा? थीटा 0 पर इसकी क्या वैल्यू है? 3 - 1 और थीटा पाई बाई 2 पर ये -1। थीटा पाई पर so this is a plot of 3 cosine square theta -1, and if I take the square of this, what do I get? I get this. This function, the yellow function, is 3 cosine square theta -1. या फिर फिंगर टिप्स होने चाहिए यार इस तरह के फंक्शंस को प्लॉट करना। यहाँ पे जब थीटा पाई बाई 2 है तो ये सारी चीज 0 होगी ना, to get a negative number। अगर ये ना होता तब आपका हमेशा पॉजिटिव रहता, लेकिन since you are going negative as well, but the purple is the square, the purple is by 2 0 squared, and we only need to go from 0 to pi because these are the possible values of theta। अच्छा, अब हम ये देखें कि there are certain points where the probability density or 3 cosine square theta -1 square goes to 0. What are these points? What is this value of theta? Pi by 2, pi by 4. When is the function equal to 0? Pi by 2, pi by 4, pi by 3. किस तरह आप कह रहे हैं? You have to equate this to be equal to 0. When you equate this to be equal to 0, theta for the 0 turns out to be cosine inverse 1 over under root 3. This is about 57.4 degrees. Now this is a very interesting angle, so interesting that it has been given the name magic angle. If you make a cube, you make two body diagonals, the angle between those body diagonals will be this angle. This is the root of this Legendre polynomial. That is, this angle solves this equation when you equate it to 0. Now let's plot a polar diagram based upon this purple curve. Why? कोशिश करें पोलर डायग्राम बनाने। when theta is 0, you get maximum, and when theta equals 57.4 degrees, your lobe goes to 0. So if I draw 57.4 degrees, then my lobe at this angle has to go to 0. And then between 57.4 and 90 degrees, I get another smaller lobe. And then I keep on advancing the value of theta. And then I twist it around the z-axis, because there is no phi dependence. There is no phi dependence whatsoever. This is what I get. So I have to twist this around the z-axis to complete the picture. There is no phi dependence, therefore I can twist it around the z-axis. Now this is an orbital which chemists call the z-square orbital. And this purple line, and there are two purple lines. These are planes at which the probability density goes to 0. These are called nodal planes. Again, since this has a z character in the orbital, the probability density maximizes around the z-axis. In the px and the py orbitals, the probability density is minimum around the z-axis. Likewise, I can construct 5 different kinds of d orbitals, and you can do this as a homework. You can construct dx, y, all kinds of orbitals you can think about. So now what we've done is we have a physical, mental, satisfying, soothing picture of orbitals. We know how orbitals come about. In our next lecture, we'll introduce the radial part of the wave function and see how 1s is different from 2s, from 3s, how 2p is different from 3p, and so on.